So guys, let's begin today's stream. Just a So what we're looking at today, let's see, market is up. It's a sharp up. Gold is now, it's coming up, literally. You see, it's sideways, no point. Can keep an eye on the it's sideways, even can pop out. Take is the tenants bank. Point we change means the quantity. The brokerage will be around 0.5 to 1.47. 0.17 to 2. I'm gonna try this. Charge.
You're never gonna make it, you're not good enough. There's a million other people with the same stuff. You really think you're different? Man, you must be kidding. Think you're gonna hit it, but you just don't get it. It's impossible, it's not probable, you're irresponsible. Too many obstacles, you gotta stop it, yo. You gotta take it slow, you can't be a pro. Don't waste your time no more. Who the fuck are you to tell me what to do? I don't give a damn if you say you disapprove. I'm gonna make my move, I'm gonna make it soon. And I'll do it cause it's what I wanna fucking do. Cause all these opinions and all these positions, they come in millions. They blocking your vision, but no, you can't listen. That shit is all fiction, cause you hold the power as long as you're dreaming. There's no way that you make it. And maybe you can fake it, but you're never gonna make it. Are you just gonna take that? Make them take it all back. Don't tell me you believe that. Are you just gonna take that? Or will you fucking fight back? Fight back. You ain't gonna make it, you ain't never ever gonna break it. You can never beat them and they're better than you face it. Thinking that they give a damn, you're not thinking straight, kid. No, they don't give a damn, you got what I'm saying? I'm not fucking playing, I'll give it to you straight, man. There's too many others and you're not that great, man. Stop what you're saying, stop what you're making. Everybody here knows that you just faking. Nah, I don't wanna hear it anymore, I don't wanna hear it anymore. All these fucking thoughts, they are not what I need anymore. I'm about to shut the motherfucking door on all you poor ass haters with your heads in the clouds, talking out loud so proud. You better shut your goddamn mouth before I do more speak out. It's about to head south. Never gonna make it. There's no way that you make it. And maybe you can fake it, but you're never gonna make it. Are you just gonna take that? Make them take it all back. Don't tell me you believe that. Are you just gonna take that? Or will you fucking fight back?
Moving on to LCM and HCM and count. So count will become 3. Now as n is 0, we break out of the while loop and return count. So we return 3. Next, let's look at the recursive solution. Coming to the recursive solution, we have this base condition that if n is 0, we return 0. And we need to maintain a stack for each function call. Taking the same number 123, since it is not 0, we go to the return part and call 1 plus count digit 123 by 10. So n will then become 12. Similarly, the next two recursive calls will look something like this. After the third recursive call, we will have n as 0 and the base condition will be satisfied. So 0 will be returned to this call. Then 1 plus 0, that is 1, is returned to this call. Then 1 plus 1, which is 2, is returned to this call. And finally, we return 1 plus 2, that is equal to 3 to the calling function, and that is exactly our output. Now, most of you might already be familiar with the iterative and recursive solutions. However, there is another one-liner solution, which is the logarithmic solution. We can use log base 10 to count the number of digits of positive numbers. The digit count of n will be equal to upper bound of log n base 10. So, log of 123 is around 2.0.
What the fuck?
That if n is 0, we return 0. Similarly, the number is returned to this call. Our output count of n will be equal to upper bound of 2.0.
What the fuck is wrong with this video?
Iterative and recursive solutions. However, there is another is returned to this call. Then solution to upper bound of
क्या यार कांट होगा भाई.
Remaining, and when you get 0 remaining, you come out of the loop. So this is the idea. Say we have number 7, 8, 9. In the first iteration, we do x equal to x by 10, so we get 78. 9 goes away, right? And we increment the result by 1, so we get the result as 1. In the second iteration, we again do x equal to x. We increment the result by 1, becomes 0. We increment the result, and result becomes. And please note that the same code can be used for both C++ and Java. The syntax in both C++ and Java. In both C++ and Java, you can write a main function. You can call this count. And complexity of this implementation. Times. So if you have number of d digits, then it's going to run d times. So if d is the number of digits in our input number, then it's going to take theta d time overall. We again do x equal to x by 10. So how do we compute the given reverse of given number? For that, we have already discussed the logic. We are going to take the last digits one by one, and then we are going to remove the last digit. And of last digit is really easy. Let us talk about this problem. We are given an integer x. Our task is to count number of digits in this number. For example, so our output an integer x is an argument and returns result, which is count of. How do we compute the given reverse of given number? For that, we have already discussed the logic. We are going to take the last digits one by one, and then we are going to remove the last digit, and then we are going to update the reverse. But we need our original number at the end, right? So we can't remove the last digit of given number. Due to this reason, we create another number temp. In this temp, we first store n, and then we get the last digit of temp, and then we remove the last digit of temp. So that when we try to get the last digit next time, we have no previous last digits, right? So let's see the working of this function with this example. This is not a palindrome number. At the end, you will get the reverse as 3554, and they are not same, so this expression will return false. Let's see how are we getting this reverse number. So we have initialized reverse as 0, and we have initialized temp as the same number. Now we are removing last digits one by one from the temp, and we are updating the temp, and we are also updating the reverse. So first thing we do is we get the last digit in a variable ld. So ld is last digit of this number 3, and then we update reverse. Reverse was initially 0, now it becomes 0 into 10 plus 3, which is 3. And then we update the temp, temp equal to 10 by 10. So last digit removes. Now our temp becomes 455. In the second iteration, we do the same thing. Our temp is now 455. we get the last digit by doing temp percent 10. We get the last digit as 5. Then we update the reverse as 3 into 10 plus 5, 35. And then we remove the last digit by doing this operation. So our temp now becomes 45. In the third iteration, we get the last digit of remaining number, which is 45. Right? Doing temp percent 10 will give us last digit as 5. 355 into 10, 3550 plus 4, 3554. And then we do temp equal to 10 by 10. So 4 by 10 now becomes 0. And when temp becomes 0, we come out of this loop. Let us talk about this problem. We are given a number n. Our task is to find factorial of n. And it is multiplication of all numbers from this 24. It is 5 into 6. Return equal to 0. Now please pause this video and try to write down. Here we will talk about a recursive solution. So the idea is super simple. We have a number n. We need to multiply all the numbers from 1 to n. So we initialize our result as 1. We go from 2 to n and multiply every I with the result. So finally we have multiplication of all the numbers from 1 to n. And if you see this example n equal to 5, we have initially result as 1. When I is 2, result will become the time complexity of the solution. This solution is simply having a theta n loop. This loop mainly runs n minus 1 times. So the time complexity of the solution is theta n. And how much auxiliary space it requires? It's not creating an array or any data structure of size n. It's simply using constant excess space. So this auxiliary space requirement for the solution is big O of 1. Now please pause this video and try to write down a recursive solution to find factorial of a given number. We can do it recursively. We can compute the factorial of n minus 1 and multiply the result of this recursive call with n. And that's how we can get factorial of n. So that's what we've done here. We take a number n and we multiply it with factorial of n minus 1 to get the result. Now, when you're reducing n by 1, for example, n is 5, you will reduce it to 4, then 3, then 2, then 1. So there will be a point when you reach 0, right? You will always reach 0. And our assumption here is n is greater than or equal to 0. This function is not going to work if you pass a negative number. So we have a positive number or a 0. And if you have such a number, and if you're reducing it by right, with this assumption. So when you reach 0, you simply return 1. That's the base case for recursion. So when you begin with factorial 5, what will happen? It will call for 5 into factorial 4. So it will mainly call for factorial 4, wait for the result to come so that it can multiply it with 5 and return the result. Factorial 4 will wait for factorial 3, 3 will wait for 2, 2 will wait for 1, and 1 will wait for 0. When the control will come here, it will fall into the base case and it will return 1 to its parent. And parent will take this 1, right, and multiply with this 1, and parent will return 1 into 1 to its parent. And now factorial 2, what it will do? It will do 2 into 1. Now factorial 4 will return 4 into 6, 24. 120. So that's how you get the factorial 5 using this recursive function. Let us now talk about time complexity of this recursive solution. So I can write the time complexity recursion formula as Tn equal to Tn minus 1 plus theta 1. You pass a variable n, it makes a recursive call for n minus 1, and then it does theta 1 or constant extra work, which is checking this condition doing the multiplication. So I can make a recursion tree of this recurrence like this, theta 1, theta 1, theta 1, theta 1 work that you are doing at every level. And this level is for n, then for n minus 1, then for n minus 2, and at the end you have for 0. So how many levels we have? We have n plus 1 levels. And how much work we are doing at every level? Constant work. So n plus 1 into constant is theta of n. So this solution, this recursive solution also takes theta in time. But if you compare it with the iterative solution was theta n, but it was taking theta 1 auxiliary space. But this recursive solution is going to take theta n auxiliary space, because there will be a moment when you will have n plus 1 auxiliary space. But the iterative solution was theta n. This recursive solution also takes theta in time. But if you compare it with the iterative solution was theta n, but it was taking theta 1 auxiliary space. But this theta in time. But 1 into constant is theta of n. So this solution minus 1, then for n minus 2, and at the end you have for 0. So how many levels we have? We have n plus 1 levels. And how much work we are doing at every level? Constant work. So n plus 1 into constant is theta of n. So this solution, this recursive solution also takes theta in time. But if you compare it with the iterative solution was theta n, but it was taking theta 1 auxiliary space. But this recursive solution is going to take theta n auxiliary space, because there will be a moment when you will have n plus 1 function calls in the function call stack. And these n plus 1 calls will take theta n auxiliary space. So this recursive solution requires theta in time, causes extra overhead. That's why our previous iterative solution is considered better. Let us talk about this problem. We are given a number n. Our task is to count trailing zeros in factorial of this n. For example, if n is 5, then its factorial is going to be 1 into 2 into 3 into 4 into 5. Now, if I compute this value, I am going to get 120, and 120 has one trailing zero. Let's see another example. If n is 10, then we are going to get 1 into 2 into 3 into 4, 5, 6, 7, 8, 9, 10. And if we compute this value, we are going to get 3628800. And this number has two trailing zeros in factorial. If you take n equal to 100, you are going to get a huge number with 24 trailing zeros. So our output is 24. Now, please pause this video and try to write down a function that takes an integer n as an argument, returns another integer, which is count of trailing zeros in the given number n. Let us first talk about a naive solution to solve the problem. The idea is simple. We first compute factorial of the given number. After computing the factorial, we count how many trailing zeros this factorial has. So for computing the factorial, we initialize the factorial as 1, then we run a loop from 2 to n, and inside the loop we multiply the factorial with I. Right? So we get 1 into 2 into 3 into 4 and so on till n. And after we computed the factorial, we initialize the result as 0. And while the factorial is divisible by 10, right, we divide the factorial by 10. And while it is divisible, we keep on incrementing the result also. And at the end, we return the result. So if n is 10, we are going to get this as factorial. Then we are going to do two iterations. In the first iteration, we are going to remove the 0 and increment the result. In the next iteration, we are going to remove the 0 and increment the result. Right, so the result now becomes 2. And at the end, we return the result. Let us now talk about time complexity of the solution. So this solution clearly takes theta in time, because we have a theta in loop here, and this is less than theta in. So we can say overall time complexity is theta in. The major issue with the solution is it's going to cause overflow even for slightly higher values of n. For example, when you have n equal to 20, the factorial is going to have 19 digits in it, right? And 19 digits may not be stored in your data types or data types like int. So please pause this video and try to think of a solution which does not have overflow issues and has time complexity less than theta n. Let us now discuss the idea for efficient solution. The idea is to count how many 2s and 5s we have in the prime factorization of the given factorial. So if you have a number and you want to count how many trailing zeros this number has, if you write down prime factorization of this number, and if you count how many 2s and how many 5s I have, and if I consider both 2s and 5s as pairs, I can count how many trailing zeros I'm going to have, because 2 and 5 together form a trailing zero. So in case of factorials, I'll write the factorial this way, and if I can somehow count how many 2 5 pairs I have in the factorial in the prime factorization, I can count the trailing zeros. And here is one more interesting fact about factorials. The number of 5s are going to be less than number of 2s. So I simply need to count how many 5s I have in the prime factorization. Let's see this factorial example. I have written general factorial here, 1 2 3 4 5 or 2n. And if I want to count how many 5s I'm going to have in the prime factorization of this factorial number, which is multiplication of all, I can notice that every fifth number here that I've written is going to have 5 as a prime factor, right? So I'm sure that if I am having a number n, then there are at least n by 5 5s in the prime factorization, because this number has a 5, this number has a 5, then 15 is going to have a 5, then 20 is going to have a 5, then 25. But I'm saying at least, not exact. Why? Because there are some numbers which are going to have more than 1 5 as prime factors. For example, number like 25. Right, there's a number 25 here, right? And then we have n. So 25 has 2 5s as prime factors. So we need to consider these also. Now please pause this video and try to write down a complete generalized formula and a generalized implementation that counts trailing zeros using this idea. Here is general formula. We do n by 5 floor, right? This is floor function. Then we do n by 25 floor, then we do n by 125 floor. So when you do n by 5 floor, it counts 1 1 prime factor of all the numbers which are multiple of 5. And the numbers which are like 5, 10, 15, 20, they have only one factor only, and they counted that. And we have also counted one prime factor of 25 as well, and we are yet to count one more prime factor. So to count one more prime factor, we consider every 25th number as well, and we increment the count for every 25th. And when you're counting every 25th number, you are counting actually two prime factors of 125 as well. One prime factor you counted when you did n by 5, and one more prime factor you counted when you did n by 25. The third prime factor can be counted when you do n by 125. If your number n is greater than 125, right? If your number is greater than 125. Otherwise, you can stop here. If n is say 24, then you can stop here. If n is say 100, then you can stop here. If n is 124, you can stop here. If n is 127, then you can stop here. That's your count, right? So now you get an idea. You get a formula, right? We can stop this formula when we get a 0, whether we get a 0 here or later, we can stop. So now please implement this formula, write a function that takes number n and returns count of trailing zeros. Let us now see implementation of the efficient approach. So what are we doing here? We initialize a variable I with 5, right? And we are multiplying I with 5. So we first compute n by 5 and we add it to the 0, right? Initially result is 0. Then we compute n by 25, because in the next iteration I is going to become 25, and we add it to the current result. Then we compute n by 125 and we add it to the result, right? That's what we are doing in every iteration. We are multiplying I with 5 and we are adding n by I to the result. So let's do a try run with this example. Say n is 251, our result is initially 0. In the first iteration I is 5, so we are going to do 251 divided by 5, and when we are doing integer division, it's anyways going to give us floor, right? So we are going to get 251 divided by 5 and floor, because it's an integer division, we are going to get 50. So our result becomes 0 plus 50, 50. In the next iteration, we get I equal to 25, right? So 251 and we add it to the result, right? That's what we are doing in every iteration. We are multiplying I with 5 and we are adding n by I to the result. So let's do a try run with this example. Say n is 251, our result is initially 0. In the first iteration, I is 5, so we are going to do 251 divided by 5, and when we are doing integer division, it's anyways going to give us floor, right? So we are going to get 251 divided by 5 and floor, because it's an integer division, we are going to get 50. So our result becomes 0 plus 50, 50. In the next iteration, we get I equal to 25, right? So 25 we divided by 251, 251 divided by 25 is going to give us 10, right? It's an integer division, so it's going to give you floor, so you get 60. In the third iteration, you get 251 divided by 125, so you get 2. So the result becomes 62. You do not have any more iterations, because after this, your I becomes 625, and 625 is more than 251. So we run this loop while I is smaller than or equal to n. This is how we get our result. Now let's analyze the time complexity of the solution. We begin with I equal to 5. In the first iteration, I is 5 raised to the power 1. In the next iteration, we are going to multiply I with 5. So I is going to become 5 raised to the power 2. In the third iteration, I is going to become 5 raised to the power 3. So if this iteration happens k times, then 5 raised to the power k is going to be smaller than equal to n, right? So how many iterations we have? We'll have k is smaller than equal to log base 5n. So the time complexity of the solution is theta of log n, right? If k is the number of iterations we do, then k is smaller than or equal to log 5n, log base 5n. So we have the time complexity as theta of log n. So this solution has less time complexity than the previous solution and solves the major issue of overflow. We are not going to have overflows here, because we are not computing the factorial. We are dividing the given number with multiples of 5 here. Hi, in this video we are going to talk about greatest common divisor problem.
Always do it on my own, so I gotta get through it. And the only thing I know is to love what I'm doing. Never give up, never slow, till I finally prove it. Never listen to the no's, I just wanna keep moving. Keep my head up when I act, head up, that's a fact. Never looking back, I'ma keep myself on track. Keep my head up, staying strong, always moving on. Feel I don't belong, tell my thoughts to move along. Push myself to be the best, die with no regrets. Live with every breath, see my message start to spread. And I had so many dreams, then you hit your teens. Life ain't really what it seems, try to find out what it means. Always do it on my own, so I gotta get through it. And the only thing I know is to love what I'm doing. Never give up, never slow, till I finally prove it. Never listen to the no's, I just wanna keep moving. Yeah, I put out all this art, it's my only medicine. Yeah, everything I do, I'm just being genuine. Yeah, I'm sick of being screwed, feel my own adrenaline. Yeah, I do just what I do, and I hope you let me in, yeah. I'm grateful, oh yeah, able, oh yeah, I'm stable, oh yeah, no label, oh yeah, you know me, I have only a path, I'm lonely, but damn, I'm going to I don't want no fake love, I want the real stuff. Everybody listen up, cause I'll only say it once. I'm gonna show you all the path, if you want it bad. I'm gonna show you where it's at, yeah, how you can get it back. Yeah, cause I ain't never done, I'll be number one. Working hella hard until I get just what I want, yeah. Rises like the sun, yeah, fatal like a gun. Shooter's gonna shoot and I'm gonna shoot until I won, yeah. Always do it on my own, so I gotta get through it. And the only thing I know is to love what I'm doing. Never give up, never slow, till I finally prove it. Never listen to the no's, I just wanna keep moving. Yeah, I put out all this art, it's my only medicine. Yeah, everything I do, I'm just being genuine. Yeah, I'm sick of being screwed, feel my own adrenaline. Yeah, I do just what I do, and I hope you let me in, yeah. Grateful, oh yeah, able, oh yeah, I'm stable, oh yeah, no label, oh yeah, you know me, I have only a path, I'm lonely, but damn, I'm going to win, yeah. Yeah, she's got some nice long hair, and you know that she's a bad chick. All the boys stare, can't help it, it's a habit. Clothes that she wears, short skirt and a jacket. I just wanna get her all alone on a mattress. I just wanna have it, I just gotta have it. Rumors all around say her body is fantastic. All natural, not a piece of fur is plastic. Head to her toes, yeah, they say that she's a latch. Yeah, the whispers all around say she has a reputation. Don't believe it till I see it, so I want a demonstration. And I've always learned it better with a hands-on education. So I need a private session, if you get what I am saying. And they say that she's not easy, no, she's really complicated. But that only makes it better, and it's got me so fixated. And I'm not the type to wait around, I've never hesitated. But she's got me captivated, so the game, I'm gonna play it, yeah. Got a body like a goldfish, she likes to keep the party going. These rumors got me feeling lonely, I want that body, baby, show me. She's got a body like a cocaine, she likes to keep the party going. These rumors got me feeling lonely, I want that body, baby, show me. I heard you look good when you're undressed. I heard you like to get away. I heard you like to stay out late. I heard you had a couple boyfriends. I heard they didn't treat you right. I heard you're hated by your girlfriends, 'cause all the guys want you tonight. Yeah, they say she's too hot, they say she's too cold. Where she came from, nobody really knows. They say she looks young, but say she acts old. From everything I've heard, she gets out of control. And all the boys say she was sent from the heavens, but I'm not too sure that this girl is a blessing. She's got the devil's eyes and they'll cut you like a weapon. She's stuck in my mind like a bad obsession. Got bad intentions. She got a body like a coffin. She likes to keep the party going. These rumors got me feeling lonely. I want that body, baby, show me. She's got a body like a coffin. She likes to keep the party going. These rumors got me feeling lonely. Body, baby, show me.
That's what's going up. How about a channel?
But it's too late now. I remember you and me, and how careless we could be.
All day and all night, we'd stay up, it felt so right. We were so young, we were so dumb. We would get drunk and then hook up. We were okay, we were alright. Staying awake till the sunrise. We were in love, couldn't stop us. Like a good drug, never run. We hook up in my car, driving so far. Play your guitar, you'd show me your art. Let down our guards, think with our hearts. Stare at the stars, we were never apart. Drinking too young, way too much fun. Out in the sun, hoping when it's gone. Took you to prom, dance to our song. Dance all night long till the lights come on.
How careless we could be. How careless we could
It's
be.
too late now. I remember everything and how careless we could be. And how careless we could be. Be.
I got it. I got it.
How careless we could be. Late nights, long fights, it felt right, we were alive. We would go out, we were so loud, we were so proud, we had no doubts. Weekends and weekdays, we'd spend our own way. We were careless, we were fearless, we were reckless, time was precious. We loved to waste time, whiskey and wine, drinking all night. by your side, finally arrived. We would just drive, never arrive. Our journey was live, staying out late, testing our fate, running away. We live for today, young and so bold, never get old. Screw what we're told, we can't be controlled. It's too late now, I remember everything, and how careless we could be,
This stall was at 271
and how careless
two, it's
we
too hard.
could be,
It's crazy to 71.8.
and how careless we could be.
6, yeah.
And how careless we could be. And how careless we could be. And how careless we could be.
Let's give it a shot. How careless we could be.
Yeah. Everybody knows that I'm breaking down. Everybody knows I ain't faking now. Everybody knows my heart's vacant now. Yeah, she hates me now. I made mistakes, but now I don't ever wanna be alone. I don't really ever feel at home. On my own, in the zone. That's the only way I know. Feeling low, about to blow back up. Here I never let the doubt creep in. Gotta pop a couple more aspirin. I don't think I'll ever let you in. Easier to break it off as friends. I don't really understand myself. I don't really understand, need help. I don't wanna be left on the shelf. Couldn't even hear me if I yelled. It's so cold outside. I'm alone, I'm alright. It's so cold outside. I'm alone, I'm alright. It's so cold outside. I'm alone. It's so cold outside. Break down, always feel like I could break now, but I never let it take me to that place now. I won't ever let my thoughts get away now. I got better things to do, picking fate now. I just wanna be the best, call me great now. I don't know if I'm okay or insane now. I remember better days on the playground. I come my way even when I'm feeling down. I fight, even when I don't know what is right. I'ma pick a side and I'ma take pride. I will decide my fate and I will never let them tell me who I am. If you try to shake me, I'll be damned. Planet on the ground is where I stand. Never give up, that was always the plan. It's so cold outside. I'm alone, I'm alright. It's so cold outside. I'm alone, I'm alright. It's so cold. I have a dream, that's all I need. I'll make it happen with some work and belief. Know what I want, so I'll take it on. I've made mistakes, but mistakes make you strong. Let's break it down for a minute. I want the crown, I'm gon' get it. You hear me loud, man, I'm winning. Yeah, Charlie Sheen will be grinning. These ladies know that I'm sinning, and this is just the beginning. I'm closing in the ninth inning. There ain't no point in resisting. Living life like a dream, live it right, that's the thing. Every night got a team, I've been tied to the scene. Out on stage, here I'm screaming. Okay, it's a dream, and I pray as a team. One day it'll be me. If I want it, then I'll get it. Head down, don't regret it. Push myself to the limit. If I play it, then I win it. I'm just saying, I'm just living for today. For a minute, I don't stay, I just visit. Have no shame, I admit it. Looking right at me to see if I succeed, to see if I believe. They're looking up to me. They want the best of me now, best of me now, best of me now, best of me. They want the best of me now, best of me now, best of me now, best of me. I swear to God, man, I'ma make it soon. Silence all the haters as they see us making moves. I do what I want, so I got nothing to prove. Staying motivated, teaching others what to do. I'm staying focused, my mind is open. They start to notice that I'm in motion. There is no potion, you're not just chosen. It takes devotion to stay composed, man. Never stop, never stop, there ain't no time to fall. Try to live, get it up, you got one life to ball. Thinking big, never small, cause you gotta want it all. When you finally get that call, you get ready, take it on. Need a handout, I already stand out. Starting to advance now, ready to expand now. You don't have a chance now, cause we're in demand now. Make it by the grand now, feeling in command now. They're looking right at me to see if I succeed, to see if I believe. They're looking up to me. They want the best of me now, best of me now, best of me now, best of me. They want the best of me now, best of me now, best of me now, best of me.
Here you are sipping tea, listening to great music, just taking a break from all the busyness. You deserve this. But wait a minute, is this an ad interrupting your me time? Yes, it is. Upgrade to YouTube Music Premium on your app or online for ad-free music. That means more of this and absolutely no more of me. Sorry for the whole interrupting your peace thing. Get a 1-month trial on us. Terms and conditions apply.
My hands steady, I feel ready, but my legs heavy, I don't get get it? How come I haven't hit it already? Still working, I'm still learning, I'm still searching, finally earning something, finally turning something called a profit. If I hear you talking shit, don't get caught in it. I'll be popping off and hit your ass, dropping all your shit. Yeah, I promise this, I got promises. You ain't stopping this, cross my shit, you'll be knocked unconscious, bitch. That's the consequence, I got this, I will not quit. Man, I'm on it, honest. I'm gonna launch quick, then I'm gone. It's just a matter of time before I'm over the climb and moving under my prime. Just quit my 9 to 5, I'm rocking, and they watching, cause it's shocking. Dropping all these top 10 songs, no stopping. It's time to live my life, it's time to live, not die. Wish I could slow down time and just enjoy the climb. And I'm the one to get it, bro. I swear to God I'll get it, bro. So don't just let me get it. Yeah, let's go. I'm gone. Yeah, I'm the one to get it, bro. I swear to God I'll get it, bro. Hey, I ain't never giving up. Yeah, I never give up. I got this, man, I got it. I will not quit, I'm on it. Never off it. Got the block lit, I'm toxic. Spitting logic, make them nauseous. Honest, and I dust it. Never cautious, drop it. I'm the hardest. Knock, knock, bitch, watch it. I'm the fucking king of rock, bitch. Profit, spitting hot shit. I'm topic, chronic. I think I'm motherfucking lost it. Back, matter of fact, making racks where it's at. Have my back to the mat, not an act, that's a fact. We attack in a back, no react, no react. Think I'm black, off his back. While I rap, not the step, go with jab, give a crap. We're advanced, I'm the man. Gotta play it better than most brands. Goddamn, I'm a rhyme till I die. Never lie, that's a lie. I don't try, I defy. Get to die, that I'm right, yeah.
We are given two numbers a and b. We need to find out the largest number that divides both numbers a and b. For example, if you see a as 4 and b as 6, there are two numbers that divide both of them. One is 1 and the other one is 2. And the largest of these two is 2. So our output is 2. Let's see this example. A is 100 and B is 200. There are many numbers that divide both of them. 2 divides both of them, 5 divides both of them, 10 divides both of them. But the largest number that divides both of them is 100. So this is an example where one number divides itself the other number. So in those cases, the output is the number that divides the other bigger number. So 100 is dividing 200, so our output is 100. Other examples can be 15 and 30. So 15 divides 30, right? Or 15 and 45. 15 divides 45, so our output is 15. Let us see this example. In this example, there is only one common divisor and the divisor is 1. So our output is 1 in this case. Please note that if two numbers do not have any common divisor except 1, then these two numbers need not to be prime. For example, two numbers 9 and 10, they do not have any common divisor except 1, right? But they both are not prime, they both are composite numbers. There is one interesting relation of this GCD. Please note that if two numbers, so our output is 100. Other examples can be 15 and 30. So 15 divides 30, right? Or 15 and 45. 15 divides 45, so our output is 15. Let us see this example. In this example, there is only one common divisor and the divisor is 1. So our output is 1 in this case. Please note that if two numbers do not have any common divisor except 1, then these two numbers need not to be prime. For example, two numbers 9 and 10, they do not have any common divisor except 1, right? But they both are not prime, they both are composite numbers. There is one interesting relation of this GCD with this tiling problem. So if you have two numbers a cross b, and if you make a rectangle of size a cross b, then your GCD problem is finding sides of the largest square using which you can tile the whole rectangle. So you have in this example a 4 cross 6 rectangle. Your A is 4 and B is 6. The largest tile, right, largest square tile that can fill the whole rectangle is of size 2 cross 2, right? So that's why our output is 2. Please note that we can fill the rectangle using 1 cross 1 tiles also, right? But there's a larger size tile 2 cross 2 which can fill the whole rectangle. But there is no tile larger than 2 cross 2 which can fill the whole rectangle. So that's why our output is 2. So there's a good relation between this puzzle and GCD. Now please pause this video and try to write down a function that takes two numbers a and b as arguments and returns greatest common divisor of these two numbers. Let us first talk about a naive solution to solve the problem. The idea is simple. We know that the greatest common divisor can be maximum as minimum of two numbers. For example, if a is 100 and b is 200, the greatest common divisor is 100. It cannot go beyond 100. So we initialize our result as minimum of two numbers, right? In case of 10 and 15, we initialize the result as 10. Then we check if 10 divides both a and b. If it divides both a and b, then we return 10 as a result. In this case, it does not divide both a and b. So we try the next small as well, right? So you will break for 1 as well, and you will return 1 inside in this program. So the idea is simple. Start with minimum of two numbers, keep trying smaller numbers. As soon as you find a number that is dividing both of them, that's your largest number, right? Because we're trying the largest possible number and we're going one by one lower numbers. Let us now talk about time complexity of the solution. So if you're given two numbers a and b, we begin with minimum of a and b. And in the worst case, we'll never find a divisor until we reach 1. So we begin with these smaller two numbers and then we reach 1. So our time taken in the worst case is going to be proportional to minimum of two numbers a and b. For example, if your a is 7 and b is 13, so you'll begin with 7, then 6, then 5, then 4, then 3, then 2, then 1. You'll stop at 1. So you're taking time proportional to 7, right? So in the worst case, it's going to be minimum of a and b. In other cases, it might take less time, like it might stop at the first iteration itself. For example, 100 and 200. So we use bigger notation and we say time complexity is minimum of a and b. Now please pause this video and try to think of any solution which can find GCD in better time complexity. There is a standard algorithm called Euclid algorithm. We are going to talk about this algorithm now. Let us first get basic idea behind Euclidean algorithm.
modify the target to 0.75. I can take it as 69 maybe. Wait a bit. Let's see. Let's wait a bit. It's gonna. That's nice. 1.2 or 0.073 divided by 3%. That's good. It's going down and down. Oh damn. What the fuck? Completed. Oh shit. Oh shit. Ah, fuck. No way. That's about 0.6. 0.6. Doesn't go down. So 0.7. 0.72.8 minus 0.7. That's about 2.2 divided by 45 maybe. Oh damn, about 9%. That's pretty good. Oh, shit. Man. It's not sure. At the end of the day, maybe. One good trade. I guess that's all for the day. Let's do some coding and play chess. Let's just maybe let's continue the video. It was interrupted pretty abruptly.
The algorithm is based on this claim that if b is smaller than our other input number a, then GCD of ab can be written as GCD of a minus b comma b. Let's now see how is this claim true. Let g be the GCD of two numbers a and b, which means we can write a as gx and b as gy, where x and y are integers. And since g is the GCD, there should not be any more common factor between x and y. So GCD of x and y should be 1. So we can write a minus b as g common x minus y. Now we need to show that b and a minus b also have GCD as g. How do we show it? See, one thing is very clear. G is a common divisor. We have written B as gy and a minus b as g comma x minus y. Now, how do we show that G is the greatest common divisor? See, if there is a larger common divisor, then there should be one more common factor between x and y. And this contradicts this, right? So G has to be GCD of a minus b and b also. Here is implementation of Euclid algorithm using the basic idea that we just discussed. So while a is not equal to b, if a is greater than b, then do a equal to a minus b. Otherwise, b is greater than a. In that case, do b equal to b minus a. And stop when a and b become equal. In that case, you can return any of the numbers a and b as your final result. So here is the triangle. Say if a is 12 and b is 15, you are going to do b minus a, right? Because b is greater and they are not equal. So b is going to become 3. Then you are going to do a minus b because now a is greater. So you are going to get 9 and 3. Then you are again going to do a minus b. So you are going to get 6, 3. Then you are again going to do a minus b. And now you get 3, 3. Now they become equal. So you stop your loop here and then you return 3. This is basic version of Euclidean algorithm. And instead of doing repeated subtraction here, we can do modular division. We are now going to talk about an optimized version of Euclidean algorithm. Here is optimized implementation of Euclidean algorithm. So we have two numbers a and b. And if b is 0, then we return a. Otherwise, we return GCD of b, comma a modulo division b. So if you take a closer look at this, we are not doing repeated subtractions. We are using remainder after division. And if we notice the parameters, we can notice that in all the recursive calls, this parameter is going to be greater than this parameter. Because what is this parameter? This is remainder after you divide a with b. And remainder when you divide by b is always going to be smaller than b. Right? So this parameter is going to be smaller than this parameter. But in your initial call, if you pass the second parameter which is greater, right, then the first recursive call is simply going to swap these two parameters. Let's see this example. If I pass 12 and 15, then in the call what I'm going to pass? I'm going to pass 15 here and I'm going to pass 12 modulo 15 here, which is going to be 12. See, if I do x modulo y and x is smaller than y, then my result is always going to be x, right? So in the first call, it's simply going to swap the two numbers if the first number is smaller. And in all the subsequent calls, this number is always going to be greater. Here it is greater, here it is greater, here it is x modulo y and x is smaller than y, then my result is always going to be x, right? So in the first call, it's simply going to swap the two numbers if the first number is smaller. And in all the subsequent calls, this number is always going to be greater. Here it is greater, here it is greater, here it is greater. Why? Because in the recursive calls, we pass b here and we pass remainder after division with b here. So first call makes 15, 12. The second call is 12 here and remainder when you divide 15 by 12, which is 3. In this recursive call, you have 3 here, right? b goes this side and remainder goes this side. And this side we'll have 12 modulo 3, which is 0. So we get the remainder is 0. So we make a recursive call for this. And when you make a recursive call for this, this is simply going to return 3 to its parent call, because when b is 0, you simply return a. And this whole code is so elegant, we don't even need to check if a is greater than b or b is greater than a, or whether a becomes 0 or b becomes 0. We know that b is going to become 0 first. So this returns 3 here, then this call is also going to return 3 to its parent call, and this is also going to return 3. Right? So finally we get the GCD as 3. Here is one more example try run. Let's say we have numbers as 10 and 15. So in the first recursive call, we are going to pass 15 here and 10 mod 15, which is 10 here. So it's simply going to swap these two numbers. Now what are we going to do? We are going to pass 10 here and 15 mod 10, 5 here. Now we are going to pass 5 here, 10 mod 5, 0 here. So when we get 0, we return 5 to the parent call. So we get 5 here, then this returns 5 to the parent call, then this returns 5 to the parent call. So finally we get the GCD as 5. Let us talk about this problem. We are given two numbers. Our task is to find LCM of these two numbers. Now, what is LCM? LCM is least common multiple. The smallest number which is divisible by both given numbers. For example, if A is 4 and B is 6, these are our two input numbers. The LCM of these numbers is 12. 12 is the smallest number which is divisible by both 4 and 6. See, there are more numbers like 24, 48, 36. All these numbers are also divisible by 4 and 6. But the smallest number which is divisible by both is 12. Here's one more example, 12 and 15. The smallest number which is divisible by both is 16. One more example, 2 and 8. In this case, LCM is equal to the largest of two numbers. So when one number divides the other number, your LCM is largest of two numbers. Here's one more corner case example. If two numbers do not have any factor in common, is 12. 12 is the smallest number which is divisible by both 4 and 6. See, there are more numbers like 24, 48, 36. All these numbers are also divisible by 4. Now please pause this video and try to write down a function that, but in the case, then we return the result. And if they do not divide, if any of them does not divide, then we increment the result, right? And we keep incrementing the result. For A is 4 and B is 6, we'll begin with 6, maximum of 2. Then we'll go to 7, 8, 9, 10, 11. So till 11, then to be more precise, we can say A cross B minus max of A comma B. That's the time complexity we are going to have in the solution. Now, do this condition and we return the result. If we talk about time complexity of the solution, we can write an upper bound of the time complexity as multiplication of two numbers, A cross B, right? And if we want to be more precise, we can say A cross B minus max of A comma B. That's the time complexity we are going to have in the solution. Now please pause this video and try to think of an efficient solution to find LCM of two numbers. Let us now talk about an efficient solution. This efficient solution is based on this formula that multiplication of two numbers is equal to multiplication of GCD and LCM. So what we do is we use Euclidean algorithm to find the GCD, and then we compute the LCM as multiplication of two numbers divided by GCD. We have discussed this standard Euclidean algorithm in an earlier video. So for example, if A is 4 and B is 6, our GCD is going to be 2 and our LCM is going to be 4 into 6 divided by 2, which is 12. Now what is the time complexity of this algorithm? See, GCD function has time complexity as log of min of A comma B. That's the time complexity of GCD function. That's all we are doing. Apart from this, we are doing some constant number of operations. So our overall time complexity is this much. So this is logarithmic time complexity, which is much better than the solution that we discussed earlier. Discuss this standard Euclidean algorithm. That's the time complexity of GCD function. That's all we are doing. Apart from this, we are doing some constant number of operations. So our overall time complexity is this much. So this is logarithmic time complexity, which is much better than the solution Let us see this problem. We are given a number n. Our task is to check if n is a prime number or not. A number is said to be prime if its only divisors are the number itself and 0, 1. It has for a number to be prime. Whatever numbers I have written here, all the filling numbers except 1 are called composite numbers. Try to write down a function that takes a number n as input and returns a Boolean value I equal to 2 to n for other numbers from 2 to n minus 1. And if we find any of those numbers dividing n, it means n cannot be prime. So that's the simple idea. Let's see the execution of this idea for 65 or output for 65. Now talk about worst case time complexity of the solution. The worst case is going to happen when n is prime number, because in the worst case what will happen, you will check for every I and you will never find I dividing n. So you will never go inside this constant time as well. For example, if you pass an even number, it's going to return false in the first iteration itself. For in upper bound, it's going to do n minus 2 iterations in the worst case. We can optimize the solution to time complexity big O of square root of n. Now please pause this video and try to think of a solution that works. If you divide 30 by 2, you get 15, and if you divide 30 by 4, the efficient solution. The idea is, if I write all divisors of a number, I can notice that these divisors always appear in pairs. For example, divisors of 30 are 130, 215, 310, and 56. If you see this pair 215, if you divide 30 by 2, you get 15, and if you divide 30 by 15, you get 2. That's how we have formed these pairs. Divisors of 65 are 1 and 65 and 5 and 13. Divisors of 25 are 1 and 25 and 5, 5. So every divisor x of number n is going to have a pair y such that n divided by x is equal to y. Right? So if xy is a pair, then we can write x into y equal to n. And if x is smaller than or equal to y, mainly I have considered the smaller divisor of the pair, right? If I take the smaller divisor, then I can say x into x is smaller than or equal to n, right? And which means x is smaller than or equal to square root of n. So the idea is not to check from 2 to n minus 1, but to check from 2 to square root of n. And why do we need to check only till square root of n? See, if there is a divisor y, right, which is greater than square root of n, then this divisor is going to have a pair x, which is going to be smaller than or equal to square root of n. So I don't need to go beyond square root of n, because even if there is a divisor higher than this divisor is going to be having a pair, and I must have found that pair because I'm traversing till square root of n. So the idea is start from 2, traverse till square root of n. If you find a divisor, then you have the number not prime. Otherwise, checking for every number starting from 2 to square root of n. And if I find any number that divides n of the efficient approach, the code is same in both C++ and Java. The only from 2 traverse till square root of n. If you find a divisor, then you have the number not prime. Otherwise, you have the number prime if you never found a divisor. Now please pause this video and try to implement this optimized approach. Here is implementation of the efficient approach. The code is same in both C++ and Java. The only difference that is there in Java is we need to replace this bool with boolean. So in this implementation, we are mainly checking for every number starting from 2 to square root of n. And if I find any number that divides n, we say n is not prime. And if we do not find any number, then we say n is prime. So we begin a loop with I equal to 2, and we check while I into I is more than equal to n. So rather than writing I is more than equal to square root of n, I've written it other way, I into I is more than n. So while this is true, we check if n is divisible by I. If it is divisible, we return false. It cannot be a prime number. Otherwise, we return true if we come out of the loop. So when your n is 65, you are going to begin with 2, then you are going to go to 3, 4, 5. At 5, you notice that it's divisible by 65, so you return true. When n is 37, you begin with 2, you go to 3, go to 4, go to 5, go to 6, and you stop at 6, right? Because 7 into 7 is 49, which is greater than 37. And you can notice that how many iterations we are saving. In the naive method, we were running from 2 to 36. Here, we are only running from 2 to 6. Then square root of n can also be a big number. And clearly notice that we are running a loop from I equal to 2 while I is more than equal to square root of n. We can further optimize the solution. Now I'm going to talk about further optimizations. Let us now get an idea for more efficient solution. If n is large, then square root of n can also be a big number. And in the previous method, we were running a loop from 2 to square root of n, and we were checking for every number if it divides n or not. We can save many of these iterations by adding 2 extra checks. The extra checks are, if n is divisible by 2, then it cannot be a prime. We need to have a base case or a corner case to handle the only even prime number, which is 2, right? Apart from 2, all the other even numbers are composite numbers. They cannot be prime. So if I add a check for n divisible by 2 or not, I can save many iterations. And if I also add one more check, if n is divisible by 3 or not, then also many iterations can be saved. Let's see how. See, if I already checked that n is not divisible by 2 and n is not divisible by 3, right, then only I proceed to this loop. Because if I find divisible, I can immediately return that this number is not a prime, leaving the corner cases aside when n itself is 2 or n itself is 3, leaving those cases aside. So if I check for these two things, I can save many iterations. If I check for divisibility by 2, then I don't need to check for divisibility by 2. I don't need to check for divisibility by 4 also. Because if anything which is not divisible by 2 cannot be a divisible by 4 also, right? So we don't need to check for 4. Because of the same reason, we don't need to check for 6, don't need to check for 8, don't need to check for 10, 12, 14, 16, 18, 20. So all the even numbers can be skipped. We can reduce the iterations to almost half. Now if I check for n equal to 3 and divisibility by 3 also, then I don't need to check for 3, don't need to check for 6, don't need to check for 9, don't need to check for 12, don't need to check for 15, 18, and 21. So I only need to check for the numbers 5, 7, 11, 13, 17, 19, and so on. Now please pause this video and try to implement this idea. Here is implementation of the more efficient approach. So first thing we do is we check if n is 1, because 1 is not a prime number, we return false. Now we are checking for n equal to 2 and n equal to 3. Why are we checking now for these two? Because we have a condition which checks if n is a multiple of 2 or n is a multiple of 3, then return false. Why are we putting this condition? To do the optimizations that we talked about, right? To skip many iterations. And when we are doing this optimization, we need to ensure that we return false when n is 2 or when n is 3. Because if I pass n equal to 2, then this condition will fulfill and it will return false, right? So we explicitly check for n equal to 2 and n equal to 3. If n is 2 or n is 3, we return true. In other cases, if n is a divisible of 2 or n is a divisible of 3, then it cannot be a prime number, right? Because once we reach here, we are sure n is neither 2 nor 3. After we have added these base cases, in this implementation, you will notice that we are skipping many iterations. First of all, we are beginning with I equal to 5. Now we are incrementing I by 6, not by 1, right? We are simply jumping many numbers and incrementing I by 6. And what are we checking? We are checking if n's remainder with I is 0 or n's remainder with I plus 2 is 0. If any of them is 0, then we return false. Let's understand with this example. Say n is 121. So you will begin with I equal to 5 here, right? none of these cases will be true, right? It's not a multiple of 2, not a multiple of 3. When you begin with 5, you are going to check if 121 is divisible by 5 or if it is divisible by 7. If it is not divisible by any of those two, you will move I equal to I plus 6. So then you are going to try with 11. Now you are going to
नंबर प्लस 1 2 का हो गया 6 का हो गया 7 इसका हो गया ठीक है
try 121. Is it divisible by 11? Yes. So you are going to return false. You are going to say 121 is not a prime number. Let us see 1031. We begin with I equal to 5, right? 1031 is a prime number. So we are going to check with 5 and 7. It's not divisible by both. Then we do I equal to 11. It's not divisible by 11 and 13 both, right? When I is 11, we are going to check with 11 and 13 both. Then we are going to come to I equal to 17. We are going to check for 17 and 19. Then we are going to come to 23. We are going to check for 23 and 25. Then we are going to come to 29. We are going to check 29 and 31. It's not going to be divisible by any of those numbers because it's a prime number. We don't proceed further because the next number after 29 is 35. And 35 into 35 is greater than 1031. And now you can notice that instead of running from all the numbers from 2 to square root of n, how many iterations we are doing? We are only doing 5 iterations of this loop. So we save a lot of work with this more efficient implementation. If you take a closer look at this implementation, you can notice that this implementation is almost 3 times faster than the efficient method that we just discussed. We are incrementing I by 6 in every iteration, and in every iteration we are doing 2 divisibility checks, right? So we are mainly doing 1 by third work compared to the previous solution where we were incrementing I by 1 and we were going from 2 to square root of n. Right? They will give you the original number. Now please pause this video and try to write down a function that takes n as an argument and prints its prime factors. Let us first talk about naive solution. The idea is to run a loop starting from the first prime number, which is 2. So its only divisors are 1 and 13, but 1 is not a prime number. So we are going to write only 13. Let us see this example. It has multiple divisors, but the prime divisors are 3, 3, 5, 7. 9 is also a divisor of it, but we are not writing 9. We are writing only the divisors which are prime. And if you notice one thing about this output that we are producing, if you multiply all the numbers in output, you get the original number, right? Because if you're simply writing all the prime factors only, right, you won't have any multiples of these prime factors, and these prime factors, when they multiply, they will give you the original number. Now please pause this video and try to write down a function that takes n as an argument and prints its prime factors. Let us first talk about naive solution. The idea is to run a loop starting from the first prime number, which is 2, and traverse to all the numbers from 2 to n minus 1 and check if this number is prime, because we want to print only prime divisibles. If I is prime, then we check if n is divisible by I, right? We have initialized a variable x equal to I, and then we are checking if x divides I. If that's the case, we print I. Now why are we using another variable x? Because multiple powers of I can also divide n. For example, n is 12 here, right? 2 divides n and 4 also divides n. So for those cases, we are using another variable x, we are initializing it with I, and then we are doing x equal to x into y. We are taking next to next power of I, and if next power also divides, we print I one more time. If next to next power also divides, we print I one more time. That's the idea. We have factors. Let us first talk about naive solution. The idea is to run a loop starting from the first prime number, which is 2, and traverse to all the numbers from 2 to n minus 1 and check if this number is prime, because we want to print only prime divisibles. If I is prime, then we check if n is divisible by I, right? We have initialized a variable x equal to I, and then we are checking if x divides I. If that's the case, we print I. Now why are we using another variable x? Because multiple powers of I can also divide n. For example, n is 12 here, right? 2 divides n and 4 also divides n. So for those cases, we are using another variable x, we are initializing it with I, and then we are doing x equal to x into y. We are taking next to next power of I, and if next power also divides, we print I one more time. If next to next power also divides, we print I one more time. That's the idea we have in this implementation. So for n equal to 12, we'll begin the loop for I equal to 2. We'll see that 2 is prime, right? And what we'll do, we'll initialize x equal to 2, and n is divisible by 2, so we'll print 2, and then we'll make x equal to 4. Then we'll check n is divisible by 4, yes. So we'll print 2 one more time, and we'll make x equal to 8. Now n is not divisible by x, so we'll stop here. So we'll print 2 2 times. Then we'll come to 3, and 3 is also prime number, so we'll come inside, and we'll print 3, and then we'll make x equal to 9. And 9 does not divide 12, so we'll stop here. And then for I equal to 4, we'll not go inside this because 4 is not prime. For I equal to 5, we'll go inside this, but we'll not go inside while loop. So we'll never go inside this part, and we'll never print the numbers if numbers are greater than 4. We are simply going to get 2, 2, 3 as output of this program. Let us now analyze time complexity of the solution. We have a loop which is running theta n time, and then we are calling its prime function. This function is also upper bounded by n, right? So it's going to take big O of n time, and then we are running one more loop inside it. And inside this loop, we are starting with the number x equal to I, and then we are checking if n is divisible by x, and then we are incrementing x with x into I. So when you have such a loop, this loop can take at most big O of log n iterations, right? This x can reach up to n, and it is multiplying itself with I to reach n. So in those cases, it's going to take at most log n steps. So we have log n steps here, and then we have n square steps here. So an upper bound on time complexity is going to be big O of n square log n. Now please pause this video and it is multiplying itself with I to reach n. So in those cases, it's going to take at most log n steps. So we have log n steps here, and then we have n square steps here. So an upper bound on time complexity is going to be big O of n square log n. Now please pause this video and think of an optimized solution to solve this problem. Let us now talk about ideas for the efficient solution. The first idea is divisors of a number appear in the form of pairs, and this idea has been discussed in prime number checking video also. So this is the same idea that we discussed there. For example, if there is number 30, and if I talk about all of its divisors, I can notice that 1 and 30 are two divisors. They form a pair. If you divide 30 by 1, you get 30, and if you divide 30 by 30, you get 1. Similarly, we have other pairs: 2, 15, 3, 10, 5, 6. So if I consider a pair xy, then I can write xy is equal to n. That's how these pairs are. And if I consider the smaller of these two divisors, smaller or smaller than equal to of these two divisors, then I can say x into x is smaller than equal to n using this and this. And from this I can conclude x is smaller than or equal to square root of n. From this I can conclude that if I traverse from 2 to square root of n, 2 to square root of n, I will get a prime divisor if there is a prime divisor, right? Prime divisor other than 1 and the number itself, then I'll get a prime divisor, right? If I simply go from 2 to square root of n. This is one conclusion. And this is the same conclusion that we use in prime number checking video as well. Let's now talk about the other important fact. And this is the main basis behind the algorithm that we are going to talk about. So we can write the given number as multiplications of powers of prime factors. For example, 12 can be written as 2 raised to the power 2 multiplied by 3. And its prime factors are 2 and 3. 450 can be written as 2 raised to the power 1 multiplied by 3 raised to the power 2 multiplied by 5 raised to the power 2. These three are prime factors. 3 appears 2 times, 5 also appears 2 times. We can write any number as multiplication of powers of prime factors. And if the number is prime, we can write the number as itself, right? 13 raised to the power 1. So the main idea that we are going to use in this algorithm is find the first prime factor. And you are sure that the first prime factor, if there is a prime factor other than the number itself, then the first prime factor would be in range from 2 raised to square root of n. So if there is a prime factor, you will find in this range. And once you find a prime factor, you are going to divide the number by this prime factor repeatedly while the number is divisible. So for example, if you have the number as 12, you will find the first prime factor as 2, right? And you will notice that 12 is divisible by 2 times. So you are going to divide 12 2 times and you are going to print 2 times. And after that, you are going to reduce your number to 3. And if you see this example, you will find the first prime factor as 2. You will divide 450 by 2, you will get 225. Then you will divide it by 3 2 times because it's divisible by 3 2 times. Then you will get 5 square. Then you will divide this number 5 square, which is 25 by 5. And you will notice that you can divide it by 2 times, right? Because it's divisible by 5 raised to the power 2. So that's how you are going to follow. You are going to find the first prime factor. So what we've done here is we first check if n is smaller than or equal to 1, then we return. Please note that there are no prime factors for 1 because for prime factors the conditions are the number should divide it and it should be a prime number. So 1 itself is not a prime and 1 is the only number that divides 1. So anything which is 1 or smaller than or equal to 1, we will simply ignore it. For other numbers, we'll run a loop from I equal to 2 and we'll run the loop till square root of n. So instead of computing square root of n, I have written I to I smaller than or equal to n and then I plus plus. And if current number divides I, then we are going to print I. See, this print syntax can be replaced with cout in C++ and system.out.print in Java. So we print I and then we do n equal to n by I. We keep doing it while n is divisible by I, right? And once we come out of this loop and if now our number is greater than 1, then we print the number. I'll talk about this corner case with another example. Let's understand the execution of this code with this example 450. We have discussed earlier that 450 is 2 raised to the power 1 into 3 raised to the power 2 into 5 raised to the power 2. So what we do in this execution of this logic is we first take out 2 and we know that if 250 is not a prime number, then its first prime factor is going to be present from 2 to square root of n. So we find the first prime factor as 2. We divide n by 2. So our remaining number is now this 3 into 2, 3 raised to the power 2 multiplied by 5 raised to the power 2. Now for this number, the same logic applies. Its first prime factor should be from the current value of I to square root of n. See, why are we taking current value of I? Because the loop keeps running for increased values of I. And we have already checked for numbers smaller than the current I, right? So it should not be divisible by them because if it was divisible by smaller numbers, they must have divided already. So now we begin with 3 and we find that 3 is dividing this number 450. So we take out all the powers of 3 from this and our remaining number gets the last prime factor, 5 square, right? So we take out all the powers of 3 and we print 3 2 times. So inside this loop, we are first going to print 3, then we are going to divide the number by 3, we get 75, then we are again going to print 3 and divide it by 3 again, we get 25. Now we have the number n as 25 and we have come out of this loop, so I is going to increment next time and I is going to become 4. Now we check if 4 into 4 is smaller than or equal to 25. It is smaller than or equal to 25, so we are going to get inside the loop for 4. But 4 is not dividing 25, right? So we do not go inside the inner while loop. Next time we run for 5. When we run for 5, we notice that 5 is dividing 25. So we are going to print 5 2 times. First time we print 5, then divide the number 25 by 5, we get 5. Then we print 5 and we get 1. And when n becomes 1, this condition becomes false because now I is 6 and 6 into 6 is smaller than or equal to 1, not true. So we come out of this loop, we check if n is greater than 1, no, so we don't print anything. And we have printed the required prime factors. We have printed 2, 3 2 times and 5 2 times. Let us now do a try run of one more example. Let's say n is 84. So we'll begin with I equal to 2 and 2 divides 84. So we'll print 2 and we'll reduce it to 42. Then we'll again print 2 and we'll reduce it to 21. Then we'll go for I equal to 3. 3 also divides. So we'll print 3 and we'll have n equal to 7. Now after n becomes 7, your I increments and becomes 4. And 4 into 4 is not smaller than or equal to 7. So you're going to come out of this loop. And when you come here, you notice that n is greater than 1 because n is 7 now. So you're going to print 7. So in this case, we are coming out and printing 7 explicitly. See, if your number is like this, what this logic is doing, it's one by one taking out prime factors and their powers and printing those prime factors those many times. So we take out 2, then we take out 3. And when your last prime factor, the largest prime factor, has only power 1, you would fall into this case. Because in those cases, you will not find a prime factor, right? If the last prime factor, the largest prime factor has only power 1, then the last remaining number is your prime number, right? So for a prime number, you will not find a prime factor, right? So you will have to print the last prime factor explicitly. That's why we have added this if condition. We can further optimize this code using the same idea as we discussed in the prime number video. If I explicitly handle prime divisors 2 and 3, I can avoid checking for many other numbers. And this way, I can save many iterations of this loop. Let's say the current value of n is n, and we are running this loop from 2 to square root of n. So if I have explicitly checked for 2 and 3 outside this loop, what will happen? I don't have to check for these numbers 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Because if the remaining number is not divisible by 2, then it cannot be divisible by 21. So all these numbers don't have to be checked. The only numbers that we need to check are 5, 7, 11, 13, 17, 19. So numbers like these only have to be checked. So we need to begin with 5, then we need to check for 5 plus 2, then we need to go to 5 plus 6, 11, then we need to check for 11 plus 2, 13, then we need to go to 11 plus 6, 17, and then 17 plus 2, 19. So the same logic that we wrote for prime number can be used here to save iterations in this code as well. Now please pause this video and try to write down more efficient implementation. Here is implementation of the more efficient solution. We explicitly check for divisibility by 2, then we explicitly check for divisibility by 3, then we check for remaining numbers, and when we have already checked for 2 and 3, we strike out many numbers. You can notice that we increment I by 6, not by 1, and that saves many iterations. We do almost 1/3 iterations inside this loop. So this way, if we run it for n equal to 450, we'll first print 2, then we'll have n equal to 225, then we'll print 3 2 times, we'll go inside this loop 2 times, and then we'll have n equal to 25. And after we get n equal to 25, we'll come inside this loop, and we'll begin with I equal to 5. So when we begin with I equal to 5, we'll go inside this loop 2 times, and we'll print 5 2 times, right? So we'll get 5 2 times, and after that, we'll notice that I plus 2 is not divisible by for the remaining n, because n is now 1. So we'll come out of this loop, and n is 1, so we'll not go inside this condition also, and we'll not be printing n. See, this condition, if you notice, it's greater than 3 now, not greater than 1, because 2 and 3 prime factors are already handled. So if you have a remaining prime number, it must be greater than 3. It should be 5, 7, or anything. You will get a prime number at the end, right? And this happens in the case when your largest prime factor has only 1 power. In that case, you will come here, but that prime factor would be greater than 3 because 2 and 3 are explicitly handled. Let us now talk about time complexity of the solution. This solution will go into the worst case when n is prime. When n is prime, you will not go inside this while loop, right? And you will not also go inside this while loop. So you will not drastically reduce n. So this outer loop will run theta of square root of n times, right? It's going to run theta of square root of n. We can say square root of n by 6, right? But these constants do not matter in asymptotic analysis. So we can say it's going to run theta of square root of n in case of prime numbers. We'll never execute the inner loop. See, if the number is not prime, that's going to run less times, because when you go inside this while loop, right? What you do is you divide the number n, and your n is reduced drastically, right? So for composite numbers, it's going to take less time. For prime numbers, you will never go inside the while loop and it will run all the iterations of this outer loop. And for prime numbers, you will have the time complexity as theta of square root of n. Let us talk about this problem. We are given a number n. We need to print all divisors of this number n in increasing order. For example, number is 15. Its divisors are 1, 3, 5, and 15. These are the numbers that equally divide 15. If number is 100, then we have output as 1, 2, 4, 5, 10, 20, 25, 50, 100. These are the numbers that divide 100. And 7, when you have prime numbers, you are going to have only 2 divisors, 1 and 7 itself. Now please pause this video and try to write down a function that takes a number n as input and prints all its divisors in sorted order. Let us first talk about a naive solution to solve the problem. The idea is simple. Our divisors can range from 1 to n. So we run a loop from 1 to n, and for every number I, we check if I divides n. If I divides n, we print I. So if n is 6, we are going to run the loop from I equal to 1, and 1 divides 6, so we are going to print 1 on the screen. I is 2, then 2 divides 6, we are going to print 2. For 3, we are also going to print. For 4, 4 does not divide 6. 5 also does not divide 6, so we are not going to print anything for these. 6 divides 6, so we are going to print 6, and we are going to stop at 6. See, I have written here print. It's kind of pseudocode. If you're programming in C++, you can replace this print with Cout. If you're programming in Java, you can replace it with system.out.print. Let us now talk about time complexity of the solution. This solution simply runs a loop that runs n times. So our time complexity is clearly theta n. The solution is going to take theta n time and theta 1 auxiliary space. Now please pause this video and try to think of a solution that works in time complexity less than theta n and theta 1 auxiliary space. To give you a hint, your solution is going to take theta of square root of n time. The efficient solution that we are going to talk about is based on these two facts. The taking 2 times. Smaller of 2, you can take any of the. I can conclude x is smaller than or equal to be smaller than or equal to square root of n 5. So I can find one divisor in every pair. Now try to use this idea and try to print all the divisors in sorted order. So what we do here, we run a loop from 1 to square root of n, because we'll find one divisor of every pair with this, and we'll print the divisor, and then we'll print the other divisor by printing n by I. That way we get all the divisors. So we run a loop from 1 to square root of n, and instead of computing square root of n, we have done this way. I into I should be smaller than equal to n. So this is basically going to run till square root of n. And for every I, we check if n is divisible by I. If n is divisible by I, then we print I. And we have this condition which says that if I is not equal to n by I, then only print n by I. So what does this condition mean? See, in case of perfect squares like 25, what will happen? When I becomes 5, you will print 5, but you don't want to print 5 2 times, right? So for those cases, we have this if condition. Let's see how does this code run for 25. For 25, we are going to run from 1 to 5. When you run for 1, 1 is dividing n, right? So you are going to print 1. Then this is not true. 25 by 1 is 25, and 25 is not equal to 1. So we'll come here and we'll print n by I, which is 25, right? Now we'll run for I equal to 2. When you run for I equal to 2, n is not divisible, and it's not equal. It prints all the order. The idea is to traverse the numbers from the solution is square root of n, and we want to keep the time complexity as square root of n only, and we want to print all the divisors in sorted order. Let us now see the efficient solution that works in theta square root of n time and prints all the divisors in sorted order. The idea is to traverse the numbers from 1 to square root of n 2 times. First we traverse from 1 to square root of n, and we print all the divisors in this range. Then we traverse from square root of n to 1, and then we print the divisors of n by I form for every number I. So this way you get all the smaller divisors first, and then all the greater divisors. So we have two loops. The first loop prints all the divisors from 1 to square root of n. 1 is inclusive and the square root of n is exclusive, which means if a number is a perfect square like 100, then the first loop is not going to print 10, right? The second loop begins with a square root of n and goes till n, and it prints all the divisors in the range from square root of n to n. Let's now see how does this work for n equal to 15. When n is 15, we are going to run this loop from 1 to 3, right? Because when I becomes 4, 4 into 4 is greater than 15, so we'll stop at I equal to 4. So what happens from 1 to 3? When you run for I equal to 1, 1 divides 15, so you are going to print 1. Then 2 does not divide, so you are not going to print 2. 3 divides 15, so you are going to print 3. So you get 1 and 3 on the screen, and then you stop this loop. So when you stop this loop, your I is 4, right? You stop because 4 into 4 was greater than 15. Now you begin this loop with I equal to 4. There's no initialization here. We begin with whatever is the current value of I, and we run this loop while I is greater than or equal to 1. So you begin with I equal to 4. 4 does not divide 15, so you will not do anything. Now you come to 3. Here we are decreasing the loop. When you come to 3, 3 divides 15. But this time we do not print 3, we print 5. So we print n by I, right? So we print 5 here. Now we come to 2, we decrease the value, right? And 2 does not divide, so we will not do anything. Now we'll come to 1, and 1 divides 15. So we are going to print 15 by 1, which is 15. This way we get all the divisors in the sorted order. Now what is the time complexity of the solution? This loop runs theta square root of n times. This loop also runs theta square root of n times. Theta square root of n plus theta square root of n is theta square root of n, and it requires theta of 1 auxiliary space. Let us talk about this problem. We are given a number n. We need to print all prime numbers smaller than or equal to n. For example, if n is 10, the prime numbers which are smaller than or equal to 10 are 2, 3, 5, and 7. If n is 23, then the prime numbers smaller than or equal to 23 are 2, 3, 5, 7, 9, 11, 13, 17, 19, and 23. Please note that we need to print n also if n is a prime number. Now please pause this video and try to write down a function that takes an integer n as an argument and prints all the prime numbers smaller than or equal to n. Let us first talk about a naive solution to solve the problem, and then we'll talk about efficient sieve algorithm. So in the naive solution, we have simple idea. We run a loop from 2 to n for every number. We check if it is a prime. If it is prime, then we print it. So I've written is prime here. I'm assuming that you have written is prime function, which takes an integer, returns a boolean value. It returns true if I is prime, otherwise it returns false. We talked about implementation of is prime in an earlier video. Here I've written print. So if you're programming in C++, you can replace
ठीक
print with cout, and if you're programming in Java, you can replace it with system.out.print. So what we do here, for example, if n is 10, we'll run a loop from 2 to 10, and every number which is prime will be printed because we are calling is prime for every number, and the number is prime we print it. So we get 2, 3, 5, 7 on the screen. Let's now talk about time complexity of the solution. So this loop is clearly theta in loop, and inside this loop we are calling is prime, and we talked about implementation of is prime. It was big O of square root of n time complexity. So overall time complexity of the solution is going to be big O of n into square root of n. Let us now talk about sieve of Eratosthenes algorithm to solve the problem. The idea of this algorithm is to create a boolean array is prime of size n plus 1. We initialize this array as true, and we do not care about these two entries because when we talk about primes, we never access these entries. In the algorithm, we are never going to access these two cells of this array. So initially, we have marked all the numbers as prime, everything is true. And once we complete the algorithm, the entries which are primes are going to be true and everything else is going to become false. Let's see how does this algorithm mark composites as false. It only keeps prime numbers as true. So what this algorithm does, it begins with 2, and every number that you traverse, it goes through its multiples and marks them as false, right? So we begin with 2, and when we begin with 2, its multiples are 4, 6, 8. So we are going to mark these as false. 4 is marked as false, 6, 8. 6 is already marked as false. We mark 9 as false. 12 is already marked. So we come to 15 and we mark it as false. Then we take a look at this array. The entries 2, 3, 5, 7, 11, 13, 17, and 19 are true. And these are our prime numbers smaller than or equal to 20. So we have found the prime numbers using this approach. One thing you would notice here is I have not considered 4. I have written 2, 3, and 5. Why not 4? Because 4 was marked as false when we were considering multiples of 2. And there's no point traversing for the multiples of 4 because 2 divides 4. And about improved implementations later, let's also be a multiple of 2. So they must have been marked already. So we consider multiples of only those numbers which are not yet marked. Now please pause this video and try to implement this algorithm yourself. Here is simple C++ implementation of sieve algorithm. We are going to talk about improved implementations later. Let's first discuss and understand a simple implementation. We have a function sieve that takes a number n as input, and this function prints all the prime numbers from 0 to n. What this function does, it first creates a boolean array, right? We're creating a boolean vector, and all the values in this vector are initialized as true, and size of this vector is n plus 1. See, if you're programming in Java, you can create a boolean array, and then you can use arrays.fill function to fill all the values as true. So for n equal to 9, our array is going to look like this. It's going to be of size 10, right? N plus 1 size, and all the values are initialized as true. So I have marked these two cells of this array as special because we are never going to access them. We don't care about the values inside them. Although they're going to be initialized as true, but we don't care. We never access. After we create the boolean array, we run a loop for I equal to 2 to square root of n, and if is prime I is true, it means it was never marked false so far. Then what we do is we go through all the multiples of I and we mark there is prime as false. And at the end, whatever entries are true, whatever entries remain true, we print those entries. So let's understand the implementation in this example. When n is 9, so we are going to run this loop from 2 to square root of 9, which is 3. So we are going to run this loop for 2 and then for 3. So when you run for 2, you notice that 2's entry is marked as true, right? So you go inside this if condition and you go through all the multiples of 2 and mark them as false. So what multiples of 2 are here? 9. 6 is already marked as false. We again mark it as false. 9 marked as false. It was not marked as false. Simply traverse 2 is prime from index 2, and whenever we see a true value, we print that I, right? So we are going to print 2, 3, 5, and 7, and these are the prime numbers smaller than. The smaller of two numbers in every pair is always smaller than or equal to square root of n. For example, if you consider all divisors of 30, they are 2 and 15. This is one pair, and in this pair, 2 is smaller than square root of 30, right? 3 and 10, 3 is smaller. 5 and 6, 5 is smaller. So you always have a prime factor which is smaller than or equal to square root of that number. So if a number is not prime, then it's one of its prime factors must be in this range, and if there is no prime factor in this range, no divisor in this range, then the number is prime. That's the idea we are using. So we are considering from 2 to square root of n, and for every value of I, we are simply going through all the multiples of it and marking them as false, right? Because it's one of these smaller factors, and we go through all the multiples and mark those multiples as false, right? Because these are composite numbers, they're multiple of I. So we begin with 2i, then we go till n, and then we do j equal to j plus I, right? And after this loop, we have all the primes marked as true. So we simply traverse through this loop and traverse through this array and print all.
क्या कर दूंगा, ठीक है। कौन सा मेला है, किस नाम से? ये ये करना कुछ
फॉरवर्ड करते हैं।
05
Those entries which are values true. One more interesting thing to note here is if I is prime, then it will be having value true at this point because you are considering the values in increasing order, right? So when you have reached I, you must have considered all the numbers from 2 to I minus 1 and considered their multiples. And if I did not have any of those numbers as factor, then I is definitely prime. So when you reach here, right, it means I is definitely prime, and you are considering all the multiples of I. So you're mainly considering only the prime factors and then their multiples. For example, suppose n is 16, then you will have an array of size 17. You will first consider all multiples of 2 and you will mark them as false, right? You will mark these things as false. Right, 10 and then up to 16. Then you will consider multiples of 3 and mark them as false. 3, 6, 9. Now when you come to 4, you will check for this condition first. And this condition is false, right? You need to go inside this condition. Here is we have replaced 2i with I square. Only for primes. And when we go inside this is also ensure that I is prime because we considered all these smaller numbers. So that's the idea of working of Sieve algorithm. Let's now talk about an optimization over the earlier implementation. So the optimization that we've done here is we have replaced 2i with I square. Let's see how does this work. So we are going to run a loop from I square to I square plus I to I square plus 2i and so on. Earlier when we had 2i for I equal to 5, we were running a loop for 10, 15, 20, 25, 30. Like we are beginning with 2i. Now we are beginning with 25. Let's see how does this work. When you begin with 25, you ignore these three numbers 10, 15, 20. And if you take a closer look at these three numbers, they have a smaller divisor than 5. See, we are running a loop from 2, right? So we must have run the loop for 2, we must have run the loop for 3, then we come to 5. So this has a divisor 2, this has a divisor 3, and this also has a divisor 2. The reason is simple. If there are composite numbers smaller than I square, then they will be of the form I into I minus 1, I into I minus 2, one of these forms, right? Or I into I minus 3, which means they have a smaller divisor as well, right? And these smaller divisors are already considered in the earlier loops. So there is no point remarking or marking those numbers again as false. So that's why we begin with I square. Here is our final short implementation of the optimized C. See, time complexity wise, the solution is same as the previous one. Performance wise should also be same. The only thing is we have reduced the code length. What we are doing now, we are running a loop from I equal to I smaller than equal to n. Earlier this condition was I into I smaller than equal to n. So what are we doing inside this loop? We are printing I also. We have removed the separate loop. See, when I previous one performance wise, and these smaller divisors are already considered in the earlier loops. So there is no point remarking or marking those numbers again as false. So that's why we begin with I square. Here is our final shorter implementation of the optimized C. See, time complexity wise, the solution is same as the previous one. Performance wise should also be same. The only thing is we have reduced the code length. What we are doing now, we are running a loop from I equal to I smaller than equal to n. Earlier this condition was I into I smaller than equal to n. So what are we doing inside this loop? We are printing I also. We have removed the separate loop. See, when I becomes more than square root of n, this loop, the inner loop will not run because it begins with I into I. So that way we can remove the other loop after the I square optimization. See, in the first code we can't do this optimization, but with the second code we can remove the loop because we are now beginning the inner loop with I square. So inner loop will not run when you have I more than square root of n, and you can extend this loop and you can print the prime numbers also in the same loop. So this is shorter and optimized implementation. Let's now talk about time complexity of Sieve algorithm. Time complexity of Sieve algorithm is big O of n log n. We are not going to go into the mathematical details of its proof because there is a long proof for the time complexity. But interesting thing here is this log n factor is very, very small. It's almost like linear. You can say this overall time complexity is almost like linear because log n grows very, very slow. And the naive approach that we discussed that had time complexity as n into square root of n, which is n is to the power 3 by 2. So this is much better than n is to the power 3 by 2. Into 3, this is assigned to the temp variable in this call, and in this call temp is now 9. So what it is going to do, it's going to first do temp equal to temp into temp. So it's going to do 3 into 3 multiplied by 3 into 3, and now it checks if n is even or odd. N is odd here, so what it's going to do, it's going to multiply one more 3. So that's in this video we are going to talk about computation of power. We are given two numbers x and n. Our task is to compute x raised to the power n. Let's understand the problem with these examples. If x is 2 and n is 3, our result is going to be 2 raised to the power 3, which is 8. If x is 3 and n is 4, our result is going to be 3 raised to the power 4, which is 81. If n is 0, then our output is going to be 1. If n is 1, then our output is going to be same as x. Now please pause this video and try to write down a function that takes two numbers x and n, and we simply multiply x with the result. So if x is 3 and n is 4, our result is initially 1. We are going to run this loop 4 times because n is 4, and we are going to multiply the result with 3 in every iteration. So after 4 iterations, our result will become 81, and we will return 81 at the end. The time complexity of the solution is clearly n by 2 if n is even, and if n is odd, then we can write it as x and try to think of a solution that works in theta log n time complexity. Let us now talk about the idea for efficient solution. The idea is based on this fact that x raised to the power n can be written as x raised to the power n by 2 into x raised to the power n by 2 if n is even, and if n is odd, then we can write it as x raised to the power n minus 1 into x. So if you write the power in this form, you can notice that these two terms are identical, and if I compute one of those terms, I can compute the power. Now please pause this video and try to write a function which is based on this idea and which efficiently computes the power. Here is implementation of the efficient approach. We are following the same idea. We are computing x raised to the power n by 2, and then we are multiplying this temp with itself. We store the x raised to the power n by 2 in variable temp, and we multiply temp with temp. And then we handle the even odd cases. If n is even, then our result is simply temp, right? Which is x raised to the power n by 2 into x raised to the power n by 2. And if x is odd, then we need to multiply x one more time. Let us see the trial run of this code with this example. Say x is 3 and n is 5. So first thing we do is we compute temp equal to x raised to the power n by 2. We make a recursive call here. So our parent call 3 5 call stops here, and it makes a call for 3 by 2. And when you make a call for 3 by 2, it again comes here, right, for n equal to 2 and x equal to 3. And it also does make a recursive call for x raised to the power n by 2. So it makes a call for 3 1. And this call again stops here, and it makes a call for 3 0 because 1 by 2 is 0. For 3 by 2, it again comes here, right, for n equal to 2 and x equal to 3. And it also does make a recursive call for x raised to the power n by 2. So it makes a call for 3 1. And this call again stops here, and it makes a call for 3 0 because 1 by 2 is 0. And when you call for 3 0, it falls into the base case. When it falls into the base case, it simply returns 1 to the parent call. So the parent call, which was waiting for this to finish, now has temp equal to 1. So the 3 1 call has temp equal to 1 at this point. So what is it going to do? It's going to do 1 into 1, so it's going to get 1. And now n is odd, so it's going to return 1 into 3, which is 3. So it's going to return 3. This call is going to return 3, right? And now once it returns 3, the 3 is assigned to the temp variable in this call. And what this call is going to do, it's going to do 3 into 3 first, right? And n is even now, so it's simply going to return 3 into 3. That's what it returns. And when it returns 3 into 3, this is assigned to the temp variable in this call. And in this call, temp is now 9. So what it is going to do, it's going to first do temp equal to temp into temp. So it's going to do 3 into 3 multiplied by 3 into 3. And now it checks if n is even or odd. And is odd here. So what it's going to do, it's going to multiply one more 3. So that's your final result, which is 3 raised to the power 5. That's what we wanted. Let us now quickly analyze the time complexity of the solution. See, if you take a closer look at this implementation, we are making a recursive call for n by 2. Right? Or you can say floor of n by 2, because if it's odd, then we call for n minus 1 by 2, right? So we make a call for n by 2, and then we do the constant amount of work. All this work is constant. So we can write the time complexity as Tn equal to Tn by 2 floor plus theta 1. Theta 1 for constant. And if I draw the recursion tree, I'll get this way. Theta 1 work at the top, say n is 16, then you will be doing theta 1 for 16, then you will be doing theta 1 for n equal to 8, then theta 1 for n equal to 4, then 2, then 1. So what will be the height of this recursion tree? If you divide a number by 2 repeatedly, then the height that you get is log n, right? So the height of this tree is going to be log n, and at every level of the tree, we do constant work. So log n into constant is log n. So overall time complexity of the solution is theta of log n. One thing about this efficient solution is it's a recursive solution. So it's going to have recursive function calls, and these recursive function calls are going to take space in the function call stack. And how big the recursion tree can be, how much can be the height of this? See, we just talked about it. It's going to be theta log n. So we are going to need theta log n auxiliary space. as well. Also, it's going to have overhead for the function call and return. In the next video, we are going to discuss an iterative solution that requires login time and big O of one auxiliary space. N is 2, which is an even number. So you are not